Hello guys. I'm your TA Yichen, and I'm sorry I have to teach remotely this week. Today I'm going to show some discussion about homework 5, and I hope this could help you with your midterm. So good luck with that. Let's first look at the first question. X is Poisson distribution, and calculate some probabilities. So for the first one, we can take 1 minus the probabilities from 0 to 6 for X. Okay, and here you just plug in the formula, but there are some terms to do. 10k k factorial e minus 10, which is about 8699. Okay, so here I choose this way. I take 1 minus k from 0 to 6, but you can also just take the sum of x equal to 7, 8, 9, and 10. Just depends on which way you think is more convenient. Then in part B, calculate this conditional probability. I hope you haven't forgot the Bayes formula. Let's do that. It's equal to the joint probability divided by the condition. Okay, so now we can use A in the denominator. So let's do that first. In the denominator, it is just the same formula as above. You can just use that number you got from A. And for the numerator, we have k equal to 7 to from 7 to 13, and the formula for Poisson. Okay, so that's still a lot of calculation, which is 7343 over 699. So the answer is 844. Okay, I hope you got this number, but that's nothing too important. That's just a practice for your computation skills. Then let's look at the second question. You're given a table. There are discrete random variables for x and y. Yeah, it's just an example teaching you how to interpret this table. So part A, find the marginal probability mass function of x. So first we should look at what values of x can take. So x can equal to 1, 2, and 3. So we can do first. The max function for x equal to 1. That is just the sum of all this. So it's 0.1 plus 0.15 plus 0 plus 0.05, which is 0.3. So similarly, x equal 2, we take the sum of the row. So it will be 0.5. And the 3, the sum of that row is 0.2. So that's it. Then let's come to the third question. Okay, so you have 3 kinds of chalks: white, yellow, and purple. They're independently chosen every time. Every day the professor choose the white chalk with probability 0.5, so P of white is 0.5. Yellow chalk with probability 0.4, so yellow is 0.4. Purple with probability 0.1, so purple is 0.1. So for A, what's the probability that over the next 10 days, she will choose white chalk 5 times, yellow chalk 4 times, and purple chalk 1 time? So for this way, first we can have some way like previously. To do this question, we just calculate the probabilities of this event and use some combination numbers. And I'm also going to show another method, which is going to use a multi-normal distribution you might have learned from class. So let's look at the first solution. I don't use any distribution information here. I just want to have this event for yellow. 5 whites, 5 white, 5 white, 4 yellow, and 1 purple, right? this is the event, and this the probability of this event. Remember, it's like you're choosing some color of balls and you want to have 2 yellow ball, 1 green ball, like that. Very similar questions. So here, if I want to choose 10 or 5 white balls, I have 10 choose 5, right? And with their probability of 0.5 every time. And for the after I choose 5 white balls, I have 5 balls left, and I want to choose 4 yellow balls. So 5 choose 4, and the probability to get yellow is 0.4, right? And then there is 1 ball left, so it's just 1 choose 1, which is a purple ball. So the probability is 0.1. Okay, so that's the thing, and you can calculate the answer. But the second way, I'm going to use the multinomial distribution, but they're still just the same, but it looks you're using different, like you're using new knowledge in the second solution, but actually they're the same. So here I have random variables, the x of the white ball, so it's the number of white ball, the number of the yellow ball, and the number of the purple ball, right? These three, they're following the multinomial distribution with n equal to 10, that's the total number. And there are 3 kinds, r equal to 3. The 3 probabilities are given here, p yellow and p purple. Okay, so this denoted by the number of this color of balls, chalks, sorry. I really thought this is a ball problem. Chalks got in 10 days. Okay, and they jointly follow the multinomial distribution. Then what you need to do is just to have this probability right? So if you check multinomial distribution, it will exactly give you like the same thing above. Oh no, I think they actually gives you something like 10 factorial over 5 factorial for 1 factorial and some probabilities, right? But they're still just the same. If you simplify this equation a little bit, and you will exactly get this formula. Okay, so this is a practice of the multinomial distribution. But if you can get it by the first solution, that's also fine. Okay, I forgot part B. What's the probability that in the next 10 days she choose white chalk exactly 9 times? Here we have the marginal distribution for choosing white chalks is following a binomial distribution, 10 days with probability 1/2 to get it every day. So that you just need x w equal to 9, right? You know it's binomial distribution. So the mass function when x you take the value of 9 is 10 choose 9, 1/2, 9 times 1/2, which is about 9756. Okay, you can keep the answer like this number, or you can keep it as a fraction. That's both fine, as long as your idea is right. Then in the next one, we're having some continuous distribution, continuous joint distribution, and let's start this chapter. So f is given above. First, prove f is a valid joint density function. So remember the definitions of the density function. The integration should equal to 1 and it's non-negative. So we can first check the integration of that fxy. Right, that's the definition, and we require this to be 1. But in this question, we can see that x and y, they're defined between 0 and 1. So which means this integration region can be narrowed down a little bit. So it equals to, I put the coefficient here, 0, 1, and from 0 to 1, xy plus y squared dx dy, right? So now that's this integration, and if we continue to do that, first I do this inner integration, and it gives me 1/2 y plus y squared, and then the answer, I'm showing every step clearly. So now it's proved to be, this integration is proved to be 1. And don't forget, we need this f to be greater or equal to 0. You don't have to say a lot about that. That's kind of obvious, but you have to, when it's straightforward, you at least should write something like this to tell us that you consider this condition and this f function satisfy both of them, so that it's a genuine joint density function. Okay. But if sometimes the f is not clear for us, you need to say more or show more to prove this condition is satisfied. So let's look at B, the marginal density function. Yeah. So here we just need to do some integration, but you need to specify the range, because the density function, the marginal density function of them is not defined. I mean, it's non-zero in some area, but it's zero in some other area. So you need to specify the whole distribution, not just the some function you want. So when x is between 0 and 1, then the marginal function can be got by taking the equation of the joint with respect to y, so that it will be this 0 to 1 xy plus y squared dy. And it turns out to be 6/7x plus 4/7. Okay, and it's 0 otherwise. Okay, and for y the same. When y is between 0 and 1, it's non-zero, and we can got by same method, which from minus infinity to plus infinity fxy, but take the integration with respect to x, and the answer is 12/7 y squared. Okay, and otherwise this y will be 0. So that's part B. Part C, let me have more space. Okay, find the probability p x less than y. So now their x and y, they're both random variables, and we take the inequality between them. So here, when we want to take the integration over the region x is less than y, right? For the joint density function. Okay. But this is just the idea, the definition, and to further accomplish it, we have this. So first we fix y, right, from 0 to 1, because otherwise the density function will be 0. So once we fix y, then since our area is x less than y, so if we integrate x, it should be from 0 to y, xy plus y squared. Okay. So you see the difference when we take the Euro like integration or calculate some Euro probability. The integration area there for x and y, they are independent. But in this case, since we require x is less than y, then the integration area here for x is depending on y. Okay, and then you further do that, it will be, if we do the integration inside and here, when we do this inner integration, we're treating y as a like constant, a fixed number. So here we can get 3/2y cubed dy. Okay, and then we do the integration for y, and it gives us 9/14 as the answer. So this is the probability of x less than y. Interesting. Then the next one, X is the number of tails in 3 flips of fair coin. So X is following this distribution, right? The number of tails. Y is the outcome of a roll of a fair 6-sided dice. So Y takes values from 1 to 6 with probability 1/6 for each event, for each number. Okay, and X and Y, they are independent. So this information is very important when you see some joint distribution, or when you're given two random variables and you want to combine them to study. So this independence result is very important. If the question doesn't say anything about that, then you cannot assume independence between variables. Then the question is to write down the joint probability mass function of S and Y. Okay, here, I don't know how you do that, but here we can write like this. So this is a joint mass function, but it means that X equal to A while Y equal to B, right? Which is, because they are independent, I forgot that this is independent. Okay, just because of independence, A equal to X equal to A times B, Y equal to B. Okay, so for A, X equal to A, so it's the mass function is 3 choose A, 1/2 with actually cube, right? And for the second, no matter Y equal, what is the value of B, it's always 1/6. So the answer is 3 choose A, 1/48. But you need to specify what's the range of A and B. So A, it can be 0, 1, 2, 3, right? They are the number of tails in 3 flips. So it could be from 0 to 3. And B is takes values from 1 to 6. Okay. So the last step is very important because you have this, I'm sorry. When you write this one, this A and B, they have some range, and if you take A to be too large or negative, this is not a valid probability mass function. So you have to specify them, and only when A and B take the values of this set, this mass function equal to this number. Otherwise, it's just 0. Okay, we have 2 more questions left. So 610, X and Y are independent random variables on 0, 1, and find their joint density function, and to calculate this, again, this kind of probability. So let me write down first. X is a uniform, so X is between 0, 1, or otherwise it's 0. For Y, the same, equal to 1 or 0, Y between 0 and 1, otherwise it's 0. Oh, and we have X independent of Y. Let me write the words. Independent. Okay. So that the joint function is just the product of them times FYY. Okay. So it's equal to 1 when X is between 0, 1 and Y is between 0, 1. And otherwise it's just 0. Okay, so if you have X is between 0 and 1, but Y is not in 0, 1, then the product will still be 0. So we require both of them are true. Then the joint function is 1. Then we want to have this probability, which is still X less than Y. dy. Okay, and so if I fix Y to be 0 to 1, right? Then for X, it should be 0 to Y, right? For X, the upper bound is Y, 1 dx dy, right? So this integration, and the answer is 1/2. Okay, I'm sorry, it was an interruption. Actually, this question, I think because at X and Y, they're independent. So if you can draw this thing, this area is the area when X is between Y and Y is between 0 and 1. And we have non-zero density functions in this area. And if we want to have X less than Y, we can see this line is Y equal to X. And this area, this like lower triangle, it's an area where X is less than Y. Oh, sorry, that's the other side. Sorry. So this area is the area where X is less than Y. Yes, this is correct. And now we can see the area because the density function is all 1 in this square, so that the probability of X less than Y equal to this area, the area of that. So it's equal to the area of the upper triangle. Right, so it's 1/2. But this way is by drawing the figure, and it doesn't work all the time. So probably you should like make sure you understand this idea by the integration. Okay. Okay, then the last one. So we have the joint density function. Now you know the function is defined more complicated. X is less than Y always, and they are between 0 and 2. So which means when we have X, Y is between 0 and 2, but if we have X greater than Y, then this density function is 0. So tricky. Let's look at this one. First, because X given Y, the function we want to calculate, it equals to the joint function divided by the marginal function. Okay, so that before we do this one, we have to have the marginal function for Y. Okay, it's the integration of the joint function with respect to X. Okay, this will give us a marginal function of Y. And based on this question, X is between 0 and Y. So for X, it's 0 to Y, X plus Y dx. Okay, now X is like the random variable, but Y is a fixed number. You can see it as fixed. So it's 3/8 Y squared for Y between this area. Just when you have some restriction on the area, you just keep in your mind what's the range whether you need to specify this range, and whether the density function will be different in different when the random variable take different values. So there you need to keep that in mind. Then for so for X less than Y less than 2, we have this joint function, right? Otherwise it's 0. And it is 2/3 X plus Y over Y squared. So that's it. We find the marginal distribution for Y, and then we use this conditional, density function formula, and that's it. So B, compute the conditional probabilities when Y equal to 1. Okay. So based on your finding in part A, we have when Y equal to 1, above the formula we got above is 2/3 X plus 1, right? And X less than 1 and 0 otherwise. Okay. Because this is important because now Y is 1, so the upper bound for X is 1. So that we want to X less than 1/2 Y equal to 1. Okay, we do the integration for X when from negative infinity to 1/2 dx. Okay, and it will equal to 0 to 1/2 x plus 1 dx. So it's 5/12. For the second x less than in 3 seconds. Okay, so now the same integration from negative infinity to 3 seconds. But now this time it will be a little bit special because I'll write here, see, this part. So now we take x is upper bound of x is 3 seconds, but since in our definition, x, the density function for x is non-zero only when x is less than 1. So that when we do the integration, the upper bound is not 3 seconds, it should be 1, right? Because when x is greater than 1, the density will be 0. Okay, so if you take care of that, it will give you answer 1. Okay, that's all the practices for this homework, and I think you have learned some discrete distributions and these continuous distributions, as well as you should know the joint, especially joint continuous density function. So they are very important things, and once you know all the ideas, you should make sure you know how to calculate those things and how to do the integration and how to give the correct answer at the end. Yeah. Thank you for watching the video if you have, and don't worry about the attendance. I will give you all the attendance this week, and we'll come back to in-person classroom next week, so don't forget about that. Well, that's all. Good luck for the midterm. I should stop recording.